Good afternoon, everyone. So this is me. You've already heard about me. I'm the lead developer of Collide Fleet, and I've worked on osquery since pretty much the beginning in 2014, and I'm happy to come share some of my knowledge with all of you. So we'll start with a bit of an update on what's going on with the osquery project. This represents, my opinions and insight into what's going on and isn't necessarily an official position, but hopefully will help folks understand what's going on, what to expect, and how to get involved. So just kind of a timeline of osquery. In 2014, it was created by Mike Arpaia at Facebook. Open source the same year. It was always the vision that osquery would be an open source tool to bring security capabilities to everyone. It was supported for 5 years directly by Facebook, who managed the open source community, provided releases, did lots of testing, and that changed in 2019. It's transitioned to the Linux Foundation. It's now a community support model. And we're kind of figuring out now what that means for osquery and what that means for the project. What we know is we now have releases of osquery going out again. Community changes are making it in. We're working on establishing a regular release cycle. And we're working to incorporate the feedback from the community into what's happening with osquery. So there's a lot of ways for folks to get involved with the osquery community. We meet the members of the technical steering committee along with anyone from the public who's interested. We meet bi-weekly over video chat. And I'd invite any of you who are interested in the state of osquery and the future of osquery to join us in those meetings as we begin to define what the roadmap for osquery looks like as a truly community-run project. My pitch to you is that osquery no longer has the benefit of a huge company like Facebook directly funding it. So if you're at a larger organization that benefits from osquery, think about how you can donate to the project. We're going to be looking to build some sponsorship and funding models into osquery so that we can take care of core things like putting out stable releases and having great testing infrastructure so that we can all continue to benefit from this awesome agent. And speaking of releases, if you're an organization that can put beta releases out and give us feedback on those, we would love to use that information to give better releases to everyone. So please reach out on Slack, come to these meetings, and we'll do what we can to make osquery continue to be amazing. So now we'll move on to my talk, which is osquery performance at scale. So the motivations for this talk, we know that as security practitioners, there's a lot of insight that we need to get on what's happening in the systems that we manage. And there's trade-offs in doing this. Using system resources to do monitoring and to do logging and alerting takes away from the primary purpose of those systems. So, this manifests in production as every bit of resources that we use with a tool like osquery is taking away from something that's probably contributing to our company's bottom line directly. And we're having to deploy additional infrastructure. And this has real costs. And when we look at workstations, we have employees who need to get their work done and are extremely upset if the tools that we deploy interfere with them. So osquery was built with all of this in mind. Performance has always been a top concern in osquery. And yet, it is absolutely possible to cause all sorts of problems. Anyone who's worked with osquery long enough knows you can certainly write a query that will blow up the system. So in this talk, what we'll talk about is how can we limit the performance impact of osquery, and we'll talk about using the osquery watchdog, functionality to do that. We'll talk about how to use the osquery schedule table to build monitoring of the queries that are scheduled on your endpoints, and how to turn that into insights and dashboards. We'll talk about deployment of new queries, which is often when the problems will be introduced, is when we have these new queries that are sort of unknown to our systems. When we deploy those, that's when we'll encounter these problems. So how can we do that safely? And then I'll touch very briefly on some tools that are available to help investigate the performance of queries once we've identified that there are issues, or to even do so before the issues are encountered. So we'll start with the watchdog. The watchdog is about limiting the performance of osquery. Now here's a query from the processes table in osquery. And we're looking at what does it look like when osquery D runs. Check this out. There's an osquery D running with the PID 45472. And then there's another one with the PID 45473. Its parent is the other osquery process. Have people noticed this before? So this is the watchdog. We get the watchdog process, it starts up. It starts a worker process as the child. And the watchdog manages the worker to ensure that we stay within the performance limits. So basically all of the potentially resource-intensive operations happen within the worker, and the watcher's responsibility is to monitor the worker and take corrective action, which would be killing that process when things go wrong. So the utilization of the worker process is checked on an interval, and if it exceeds the limits that we define, then that process is killed. So under normal circumstances, a worker goes to execute a query. It writes into RocksDB the backing start. You can basically just think of this writing to the file system. Information about the query that it's executing. Then it goes and executes the query. And then it removes the information about the running query. So everything worked great there, and there were no problems. Now, this is kind of a rundown of what it looks like when there's a problem. The worker writes the information about what query is running. It starts to run the query, and it consumes too many resources on the system. The watchdog process kills the worker process and then respawns a worker process. That new worker reads from the database the information that a query was executing while it was running. So it now knows that that query caused performance issues that cause it to be killed by the watcher. And so a log is output with that information, and the query is blacklisted. I'll tell you what blacklisting means in a minute. But here's what this looks like from a logging perspective. You know, osquery always tells us when it's executing a query, and we see that this starts happening, and then the watcher kills the worker process. The watcher executes a new worker process. The new worker comes up, and then it notices this query failed. And you can imagine, I mean, this query is obviously not useful, but it's creating quite a large quantity of results, and this is an easy way to get the watcher to kill a query. Just create way too many results, and you're done. And you can sometimes do that with queries that you think are actually good, especially when you get into joins, especially if you have issues with those joins or you're using tables that are processor intensive. Because remember, osquery results are generated on the fly for the most part. They're often not being retrieved out of a real database. So the performance impact of different operations is not necessarily transparent to you as a user. And so we'll talk about the options that you have for understanding that a bit better. So when the query execution fails in this way, we don't want osquery to just respawn, try that query again, and end up crash looping. So the queries are blacklisted. They're removed from the schedule for 24 hours. And this means potentially, if this is a query that was really important to our visibility, we don't have visibility anymore. But we constrained the performance impact on our systems, and that's likely more important. This is a trade-off that we have to decide in our own environment. And we can get information about which queries are blacklisted from the osquery schedule table. And we'll talk about how to use that to build monitoring and make it much easier to understand how these things are happening on your systems. I just think this is kind of cool. The way that the watchdog figures out how much utilization is happening in the worker process is it just runs an osquery query against the processes table. So that's cool. osquery uses osquery to watch osquery. And even if you weren't aware of this, you're probably benefiting from it already. The watchdog is enabled by default. And by default, you'll get these normal settings. Up to 10% of CPU can be used for up to 12 seconds. Up to 200 megabytes of RAM can be used. And just to be clear, what this means is that if the CPU utilization goes over 10% of the available CPU, and it stays at that level for longer than 12 seconds, then the process will be killed. So it can spike to higher levels of CPU, but it's that sustained CPU usage that causes the process to be killed. And there's also a very easy way to configure the more restrictive settings. 5% for up to 6 seconds and only 100 megabytes of memory, or you can disable it. And sometimes disabling it is the thing that you have to do because you care more about that visibility than the potential performance impact on your system. And further, you can customize these settings to the specific needs of your organization and the systems that you're running on. So you can set that utilization limit, and you can set the memory limit. Right now, it's not super easy to configure how long that threshold is. You just have the 10 seconds and 5 seconds option. If this is something that matters to folks, we could fix this pretty easily, but this is just what's currently exposed in osquery. And again, I want to call out this trade-off. There's a trade-off here between visibility and performance safety. So we can be really aggressive about the limits that we apply, and we can know that we will have little impact on our systems. But this may come with the trade-off of having queries fail to execute and then be blacklisted. It may be fine. If we're careful about what queries we execute, it could be fine, and we'll just be safe. But it could come with this trade-off. And if you're using osquery extensions to introduce additional functionality like tables, and I think hopefully we'll be hearing about this kind of stuff from what Stripe's been doing with the memory, you can have osquery manage the extension process, and you can get these same benefits of the watchdog over your extension process. So this safety can apply to the whole multi-process ecosystem of osquery that may be running on your machines. So once we've set up this kind of limiting, the other thing that is important to do is to have monitoring to understand what is the performance impact of the queries that we're running, what are the relative performance impacts, and are we running up against these limits that we've set? So we can, again, use the facilities of osquery to do this monitoring. And it's the osquery schedule table that provides a lot of this useful information. So while the query executes, osquery collects the performance information, looks at the system and user CPU time, looks at the memory of that process, and records that into this table. So here's the data that's available. And this is a little tricky and something I think we could improve on, but these times, the wall time is in seconds, the user time is in milliseconds, the system time is in milliseconds. And all these times are cumulative over all of the executions of the query. So if you want the average execution time, you need to divide the wall time by the execution count. Sorry, it's just a little tricky, but now you know. Memory is maintained as an average, so you don't have to do this division. We could probably do better here, but this is the state of things right now, and we can make a lot of use of it as it is. Oh, and we'll just point out, blacklisted. This is a column that lets us see whether the query has been blacklisted. No, so we do not have manual control over the blacklist, although we can set some queries. There is an option that allows us to set queries that cannot be blacklisted. Whether this is a good idea or not is something that we have to decide based on, our own needs. Yeah, we could go deep into the considerations of that. I would not recommend reaching towards that tool in a typical case. And so when we think about monitoring, to me, a first thing that I would really be interested in monitoring is which of my queries have been blacklisted, because this is going to tell me what I no longer have visibility into. And so if I have the capability for alerts, I would love to alert on any results from a query like this. So this osquery schedule table gives a lot of useful information, in particular if we can aggregate it and look at how these things are changing across hosts and across queries. So for some ideas of what you might want to put on a dashboard, you could put a list of the blacklisted queries. You could look at the average memory usage of different queries and the CPU time used by those queries. And what I found when doing this is visualizing the percentiles, like a 50th percentile and a 95th percentile, really helps with getting a more holistic understanding of the performance. So as an example, here's a dashboard that I created in a little test instance with some useful information. How many hosts are enrolled, how many unique scheduled queries there are running on all those hosts, and information about which queries have been blacklisted. And in this case, I just have this query root hash, which is hashing everything in the root directory, not recursively. So typically there's not too many files in the root directory. But on one host, there were a bunch of files. And so on that host, the query was blacklisted. So it's only one host that the blacklist is on. If this were all 7 of the hosts, then we know we have no visibility into whatever this query is showing. And then we'll dig into these charts by looking a little closer. So here we're looking at the total time taken by the queries. And again, looking at this root hash query, we note that the 99th and 95th percentile of these are really high. The 50th percentile, really low. And this is because a couple of these systems have files that I created by dumping garbage into the root directory, and the queries take a long time to execute there. However, on most of the hosts, they execute very quickly. Now, this is a toy example, but this illustrates that you can have the same query perform extremely differently on different hosts based on the state of the system. And so this is something that we have to be careful for. Then if we look at this query, this one hashes everything in user bin, and it's relatively stable across all of the hosts that we have in here, how much is in there. So we see that the time taken is relatively stable across all of those hosts. And now imagine introducing new queries and being able to compare how their performance is relative to the queries that we already have, and then use this to inform, for example, how often we might schedule the queries. We can do similar with memory. I think there's not a whole lot more insight to show you on this slide relative to the last one, but again, we can see which of our queries are using the most memory and use that to judge whether these are bringing the value that's worth it for the resource utilization on those machines. And now we'll talk about strategies for deploying new queries in a controlled manner. So like I said before, deploying in new queries is potentially kind of a dangerous time because we don't know exactly how these queries will perform. Even if we've tested them on a single host or just a few hosts, as we've seen, different conditions on different hosts can result in very different performance. So the two biggest strategies for doing this kind of rollout are segment your hosts into groups that you have control of their configuration and use that to deploy queries to individual groups of hosts before deploying them to the whole fleet. And then secondly, use the shard option in scheduled queries to slowly roll out the query even within those groups that have received the query pack. So we'll go into what each of those look like a bit. So segmenting your hosts, especially if you can do it by risk tolerance, if you have users who are willing to work with the beta software on the workstations, roll out queries to them first. If you have production servers that are typically underutilized, roll out queries to those first so that we can mitigate the risks associated with doing these things. And so there's a couple of ways to do this. If you're managing configurations with tools like Chef or Puppet so that you're laying down configuration files onto the hosts, well, then you can deploy different pack files to the different hosts, and that can be your strategy. Or if you're just using plain osquery and you don't necessarily have a good way to group the hosts and lay down different configuration files on each host, well, then you can use the discovery query capability of query packs, where you gate the execution of a query pack based on the dynamic results of a query that you specify. So you can do things like matching on the host name or looking for the MySQL process running and say this pack only executes under these conditions. And then if you're using something like Collide Fleet, we have the notion of labels, which work very similar to discovery queries, but they're maintained by a server, so we can actually see exactly which hosts will be receiving those queries. So then we have the sharding option. The shard option lets us set a percentage of hosts that receive the pack, or that receive the query, who will actually execute that query. So we can start in our lower risk servers. We can set the shard to 1, and then only 1% of the servers that receive that config will execute that query. And then where this becomes really valuable is when we have dashboards like this. So we can roll out that query to 1% of our hosts and take a look at the dashboard. Where does that query fit in the performance relative to other queries? Are there outliers? Do we need to understand more about what's going on these systems that's affecting the performance of the queries? And then we can increase the shard 1% to 5% to 10% to 50% to 100%, or whatever our risk tolerance is. And then we can deploy to new classes of machines. And again, regarding our risk tolerance, we can continue evaluating these metrics and understanding how the query is performing across all of the different machines as we do this. Yeah, so this slide is kind of summarizing what we just discussed looking at the dashboard. And then this final part is how to use the tooling that's available to us to start to debug the problems that we identify. So we have a couple of different tools for that purpose. We can use the profiling script, which will help us to run our query packs on the local machine and get some relative performance information from that machine. So we don't have to look to dashboards. We don't have to have our deployment strategies all ready to go. We can just run the pack on a local machine and at least get some sense of how those queries will perform. And we can take the query pack that we have already, add a new query in, and then see how that query behaves relative to what we've already been doing. And again, we still have this issue that queries can behave differently on different hosts, but at least this gives us some sort of baseline to understand these things. So this is what that looks like. You hand it a query pack, and you tell it where your osquery shell is. And then it will run those queries and give you these are sort of some relative numbers of how much CPU is used, how much memory is used, file descriptors, and the duration of the query execution. And we can understand how these queries perform relative to each other using this tool. And then once we've identified queries that are problematic, we can start to use the tools that are provided to us by SQLite to make sense of that and begin to optimize that. So here we have a query, not necessarily the best written query, and what we'll notice is that the processes table gets hit twice. And if I look at this query, well, okay, it's because we have this sub-select against the processes table. We're hitting processes twice. So in this case, it's a pretty obvious optimization. We can move the constraint where UID equals 0 into the outer query, and we will save. So we do that. The query has effectively the same meaning, but we've reduced substantially the work that SQLite has to do to generate the results. So that's really just scratching the surface of starting to understand and debug the performance there, but hopefully that just makes you aware of some strategies that you can use to achieve these things. So my recommendations are use the watchdog to constrain the performance of osquery on your systems. Make sure you understand what your risk tolerance is for performance and what your needs are in terms of visibility so that you know what trade-off you're making. Monitor the performance of your queries as you deploy them and on an ongoing basis, and understand which of your queries are being blacklisted, because these are the spots where you no longer have visibility. Be strategic about how you roll out new queries, because this tends to be the very dangerous time for performance. And then learn to use the tools to write queries that will perform in a way that allows us to get the insights that we need without causing problems on the systems that we manage. So that's it. Thank you.